Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about a few things. We're going to focus primarily on fog, but we're also going to look at things like dew, frost, and haze along the way. So sit back and let's learn about some things that here in the Chippewa River Valley we see a lot of as the seasons progress. So let's just remind ourselves, how does air become saturated? Well, by adding water vapor to it, by mixing cold air with moist warm air, or by cooling it to its dew point, things like diabatic or adiabatic processes. If we recall, diabatic processes, basically any temperature change of air not related to adiabatic vertical displacement. Adiabatic processes just deal with the changing temperature of a parcel of air due to the rising or sinking of it. Um, Adiabatic processes assume that no heat, mass, or momentum is passing through the boundary of our parcel. So we often see these saturation expressions as things like dew, frost, sometimes haze, fog, clouds, precipitation, things like that. Dew is just common, something we see common on vegetation early morning after a clear night. Basically, air is just cooled to its dew point. It becomes saturated. It happens on clear nights because that surface radiates heat and it is not trapped by a cloud cover. Clouds are great at insulating the surface, and if you remove that insulation, well, you have things like dew formation, and you have a more rapid fluctuation of temperature and uh, kind of cooling of the surface. Dew forms on vegetation because it cools more quickly than, say, a road surface or kind of buildings or things like that. And vegetation has a lower heat capacity per unit area. So it serves as kind of a great area for dew to form on and latch onto. So dew formation releases latent heat and reduces the rate at which the surface cools. So the dew point temperature is often the minimum nighttime temperature that you experience. Frost forms if the dew point is below 0 degrees Celsius, or what we call the frost point. White frost forms by ice deposition directly from vapor in the form of six-sided crystals. Think of your typical crystalline lattice work that you see in snowflakes and things like that. Black frost or black ice forms when the dew point is just above 0 degrees. So the dew forms first and subsequently freezes as temps drop below 0 degrees Celsius. So a layer of ice is formed without the creation of small crystallites. And then we have things like haze. Dry haze is just small particulates themselves, maybe with a little bit of condensation on them. In a dry haze, you can see things like what you see in that top right image. High visibility, but you can see it almost looks, especially once you get back, we follow our little mountain ridge down here. Once you get back past here, you can see it kind of almost looks muddled or distant. That's dry haze that we're seeing here, as opposed to wet haze, which begins with relative humidity around 75%, much more light scattering than dry. So if we look at the image on the bottom right, obviously a lot more prevalent in the landscape and the atmosphere because you're not able to see nearly as far. So that top is dry, the bottom is wet haze. So that's just kind of an idea of what that looks like. Now, move a little bit past that, we get into fog, which is where we're going to spend the rest of our video. So this is a picture I captured from Northern California just a few years ago. So fog is what happens when you go above 70% relative humidity to about 100% relative humidity. Here you've got condensation on less active nuclei along the surface. We talked about cloud uh, condensation nuclei in that last video, or condensation nuclei in general. Essentially, it's a thick, wet haze on the ground. Think of it as a ground cloud, basically. It's called fog when that visibility decreases to less than a kilometer away. We have four main types that we're going to talk about: radiation, advection, upslope, and evaporation or mixing fog. So it forms in three different ways. Again, the cooling of the air, the evaporating of water into the air, or the mixing of two air masses, resulting in saturation. Types of condensation nuclei affect fog. Over the ocean, you've got fewer drops or fewer condensation nuclei, so you end up with larger drops of fog. Over urban areas, much more smaller drops, lower visibility, Think of, the expression, the fog is as thick as pea soup, or London fog, as we see here. Those are ways to describe how poorly they are for visibility. Some chemical reactions can cause fog to be acidic, and if temperatures drop below freezing, freezing fog may result. So the first one that we're going to talk about is radiation or ground fog. So here you can see in our little diagram next to my face, you have long wave radiation and surface cooling kind of interacting. So that warm air mass and that cool air mass kind of combining, and you end up with surface fog. So that surface is radiatively cooling. It's radiating out heat over the night. We know that. We learned about that a couple of weeks ago. The light breeze helps more air contact the cold surface. So we often see this, especially here in the fall and winter. It's common in low-lying areas, again, like the Chippewa River Valley and river valleys in general. So you'll see this kind of right along the river valley, and it forms upward from the ground. It's deepest right around sunrise. It may intensify just after sunrise as you've got evaporation of the dew kind of adding to that surface cloud bank or fog. And it typically burns off when you have more insulation coming in. So as the ground is heating up, it's being heated from the top and the bottom. It basically dissipates, mostly around the edges, and then kind of as it kind of works in towards the center of the radiation or ground fog bank. And we can see that. We can see that picture up in the top. That's the Central Valley of California. Completely covered in fog. And we'll talk about this phenomena in particular here pretty soon. So favorable conditions are clear, cloud-free nights that are cold. You'll have a shallow layer of moist air near the ground, a lot of times after recent rainfall or near a wet body of water, when you have long nights and very light winds. We can see phenomena of that here. So this is our radiation fog. The next big one that we move into would be our evaporation or mixing fog. So these are formed by the mixing of two unsaturated air masses. You've got moist, basically think of it as when you're breathing, right? You breathe out on a cold day, you've got moist air coming out of your mouth, and it's mixing with the drier air, the outside. So you see that expressed as kind of evaporation fog. You could think of it as you have cold air over warm water. That was what we call steam fog. So you see this over pools or spas or, bodies of water when you have cold temperatures outside and the water is still warm for the season. Increased moisture raises the dew point, so maintained through vapor pressure difference and mixing. We can see this expressed as steam devils on a lake or precipitation fog. So if you see in this little diagram off on the right here, we basically got two different parcels, or two or three different parcels. We got A in the bottom here. We've got B here. And as those mix, you end up with C. So we are, at this point, anything below the line is unsaturated. Anything above the line is saturated. So we've breached that point where we're above the mixing ratio, so now we're in saturated air, above our line here. So contrails are another example of this type of fog. You've got the really hot air coming out of the jet mixing with the cold air around it. You see contrails. So saturation vapor pressure, if we're kind of looking at this graph here and thinking of these types of phenomena, depends on temperature. So the higher the temperature, the higher the saturation vapor pressure. We learned about that a few presentations ago. So warm rain falling into a cold air mass near the surface can form fog. Typically, we might see this as fog forming along a warm front, for example. So we can see a couple examples of this evaporation or mixing fog here. This fog formed when rain evaporates as it falls through a colder layer of air. You see that here as well. We call this precipitation fog or frontal fog. We've got contrails here, right, forming behind a plane. So cloud-like streamer, frequently observed behind aircraft flying in clear, cold, and humid air caused by the addition of atmosphere, or to the atmosphere of water vapor from engine exhaust gases. So that's part of the combustion process, is all that warm and moist and very hot air that's being kicked out by the jet engines of that plane. And then we've got over a lake, or steam or evaporation fog. So fog that has the appearance of steam and is produced by evaporation from a warm water surface into the cool air above it. And steam fog in general forms when that cold air moves over a warm water. Think of a heated outdoor swimming pool. So that water evaporates from the pool into the air, increasing the dew point, and if mixing is sufficient, becomes saturated. The colder air directly above, the water is heated from below and rises, forming what appears to be steam. You've probably seen this pretty regularly, especially around the chip or lakes or things like that. We've got things like lake effect clouds that are kind of forming as a result of some of these things. So as air is flowing over the relatively warmer Great Lakes, cold, dry air gathers heat and moisture from the surface, cools, rises rapidly, mixes. You've got these streamers that start to form, rising from the surface. Others condense to form what you see in that right over here, these stratocumulus clouds in the upper half of our mixing layer. So that's kind of one of the dominant ones we see, especially along the Great Lakes. You can see them in Superior. You can see them over Michigan as well. We've got things like Thule fog. This is a really interesting one. So this is a special kind of radiation fog that happens every winter in the Central Valley of California. So you can see San Francisco here, Santa Barbara down here, just to give you some context. LA is a little bit that way. So what you have here is a combination of cool, moist layer of air from the Pacific close to the surface, clear skies, and light winds. And this leads to an exceptionally thick fog. So let's actually look at this as it progresses over a couple of days here. So notice we are in December or December 19th in this example. You can see it actually starting to fill in. So let's kind of look again here, highlighting where it kind of, you see things starting. And now in that second one, we're pushing all the way to the bay and all the way around this form here. And then we have this incredibly dense fog that continues to thicken in just over a 2-day period. So this is what we call Thule fogs. This is pretty unique to the Central Valley, and kind of an interesting one to experience. We've got the next one here. This would be valley fog. So cold air and high moisture contents in river valleys make them susceptible to radiation fog. Radiation fog forms at the ground and is deepest around sunrise. Sometimes an increase in thickness at sunrise due to the evaporation of dew supplying moisture to the fog. So you can see this. This is another one that we typically see, especially here around the chip. Next one, we've got advection fog. So this forms due to moist air moving over a colder surface, resulting cooling of the near surface area to below its dew point temperature. Advection fog occurs over both water and land. So San Francisco experiences this a lot. That's kind of the dominant mode of fog that we see in the San Francisco area. You've got surface water near the coast is much colder than water further offshore. The moist, warm air from the Pacific is advected over the colder waters, basically leading to this advection along the surface. You can see examples of it here. We got Oakland, San Francisco. Here's that as it's coming into, or kind of just hanging right off the coast. You've got that mixing of the air there, and you're leading to these advection fogs starting to form. Here we can see the same thing just from a oblique view. We're looking at the Bay Area right up here. And same thing right here, looking over the famous Golden Gate. Now, a fun fact, this fog has been given a name. It is Carl, um, which is such a goofy thing, but it's a little bit fun nonetheless. And here we can just see a couple more examples of convection fog moving through these two different landscapes. Finally, we've got upslope fog. So think of upslope fog kind of as an adiabatic process, right? So it forms as moist air flows up an elevated plane, orographic lifting, basically. And as it flows up that elevated plane, as the air ascends, it cools adiabatically and saturates. It just doesn't rise to altitude. It's kind of stuck along the ground, which is kind of the key distinguisher between upslope fog and standard cloud at altitude. So these can actually last for days under the right conditions as you've got kind of stagnating air along that upslope front. So upslope or valley fog, we can see kind of the dominant areas of fog across the United States. Upslope fog happens especially along things like the Front Range over here. We typically see radiation fog over in the desert Southwest or in the Midwest, so Illinois, Indiana, Pennsylvania, etc. Advection fog or radiation fog coming in as you got that wind coming off of the warm Gulf of Mexico over the colder land mass of the south, and then advection fog kind of pushing into Newfoundland and New England area and Prince Edward Island, and then kind of this advection fog pushing down along the Pacific coast as well. So the Bay Area, Northern California, and other places like that. Typically on a given day, or in a given year, pardon me, the foggiest places in the United States are Appalachia, New England, and the Pacific Northwest, and also kind of the central coast area of California. We see it a bit in close to home as well. We've got some denser fog in Superior area in the Upper Peninsula of Michigan. So there you have it. We talked about dew, frost, haze, and fog in this video. In the next one, we're going to be starting to talk about clouds. So, fog at altitude, if you will. So hope you enjoyed the video, and we will see you in the next one. Thank you.